this, is gamma here. So in 4D, a priori you have a problem because you have this parameter. But then when you compute the entropy in 4D, what you get is A over 4 RT squared and gamma over some gamma 0. And this gamma 0 is fixed by the computation. This is the root of the conclusion to an algebraic equation. So then what people say is that, okay, you can recover the right result, but you set gamma to gamma 0. This is how people compute the numerical value of gamma. So in cosmology, when people compute the critical density or the volume of the universe at the bounds or something like this, we use a numerical value, which is important for this computation. But in fact, so I'm doing some advertisement. So recently I was able to show with my colleagues that you can do the computation by taking the complex value of gamma. So a priori we said that in the classical theory, if you take gamma to be complex and not real, the image group is not compact and you cannot contest the theory, it's complicated. And what you can do is, at the quantum theory, you can take gamma to be complex, then do the computation, you don't have this anymore. So you get immediately A over 4. This is consistent with so people see this gamma now really as a regulator. So because classically, if you don't put gamma, the group is not compact, you cannot quantize. People say, okay, let's put gamma, the group is SU2, you can quantize, you have the structure, blah, blah, blah. And then in the quantum theory, you have to find the right place to put gamma to I. And once you put gamma to I in the right place, you can get A over 4.
And you obtain exactly the classical result of Alpi without any correction.
Huh?
Without any correction.
No, you also
Without
have
any
corrections, yeah.
terms.
So I think if you put gamma complex, you don't get the right interactions. I don't worry too much about this because nobody really knows about these corrections. Usually I think it's 2/3, 3/2 maybe. On the log of A, but so yeah, so in fact with a real gamma, people are able to derive this the log correction that string theory people derive and that people agree on. I think it's -2/3 or 3/2 maybe, I don't remember. Something like this. And if you take gamma to be complex, you can remove this problem of fixing the gamma, but I don't think you only get -1. But this is not really. People are still working on this now too.
Other questions?
You could have added matter from the beginning, right?
In principle,
For the matter.
in principle, yes.
Yeah. In principle.
In principle, yes, because it's Hamiltonian quantization, so you can just put Hamiltonian for the matter, and then, because in some sense, the entire difficulty was to find the right variables and the right quantization for the gravitational part. But once you know how the gravitational part is quantized, it's in some sense the most difficult thing to do, and then once you couple this to matter, so people present it this way, but it has never been done really, because it's already so hard to understand, like in the gravitational sector, what happens and how to extract physics, that if you put matter, it becomes even more complicated.
So only at the level of cosmology is possible to
Yeah.
add this.
Yeah. But I wouldn't worry too much about this in the sense that, in the sense that we, even for pure gravity, we don't even know what it means to do computation of pure gravity without matter, and to structure of the theory. I presented this in a way that looks like everything is like this, but there are many, many ambiguities and stuff that we don't control and don't understand. And I think that before this is clarified rigorously, there's no need to start putting matter because it's only going to make everything more complicated. So maybe for the future, once we.
And do you think it's possible, or it would be possible to see some observational signature of this discretization this time? Or is it?
I don't really know. People first they thought about this, but this is very. So for example, the minimal eigenvalue. So this area gap in cosmology is really tiny. So we don't know what it means. So if you have a device that could measure very, very small surfaces, I don't know if it could be quantized or not. Or if it this is just an effective description of something, some phenomenon, or nothing we notice. So I think the closest way that we are to maybe testing this is through cosmology. And in fact, there's been recent papers by Ashtekar and two of his postdocs, like extending the inflationary paradigm, like in the Planck regime, so using the quantum cosmology stuff. And you have all the spectrum for the tensor perturbations, scalar perturbations, and things like this. This is the only thing that we can measure, in fact. It's like the Planck satellites only measures this type of data. So even here, even if you put data, even if you put matter in this model, you don't even know how to compute, like how to do an experiment that can test this thing, because we don't know any quantum gravitational experiments apart from cosmology. So maybe the hope is cosmology.
It's related to the first question about adding matter to your construction. I was late to your first lecture, but I was able to see on the board that you were assuming no compression. So, how do you expect to add fermions if you have no torsion? And how is that important to your construction? Because it's a part of geometry, but it will be needed if you would like to add fermions.
Yeah. In fact, it's a really, really subtle question. I think people don't agree on whether we have torsion or not. And, so first thing is if you put fermions, then you have torsion, because you put fermions from the beginning and you have source of torsion. Now the other question is whether in this framework there is torsion or not. And I would say yes, and yes, because so we saw that so classically on shell, the term proportional to gamma vanishes on half shell. So when you solve the torsion-free equation. So classically, if you have no torsion, you have no gamma term. So I think that the fact that gamma stays in the quantum theory means that the way that we handle the second-class constraints means that we don't completely solve torsion. Because the torsion, so in the Lagrangian theory, the torsion is this covariant object. This is what behind it. This has many, many components. But then at the Hamiltonian level, all the components are completely dispersed everywhere. One of them is the Hamiltonian constraint, one of them is second-class constraint, one of them is a Lagrange multiplier, and it's not clear to me how all this stuff are imposed in the quantum theory. And in fact, what I also said earlier, when I said that the loop quantum gravity phase space is bigger than the phase space of rigid geometries, is precisely because of this. In rigid geometries, you have all the triangles that have the same shape, so you can glue them together. And here they don't have the same shape. They have the same area, but not the same shape. And this is torsion, if you want. The fact that when you glue stuff together, they don't have the same shape. And if you impose this shape, you impose the remaining second-class constraints, which are the torsion. And also in spinful models, when you wrote down the simplicity constraints, if you impose this constraint classically strongly, torsion is vanishing. But since people impose them at the quantum level weakly and in a very strange way, like the EPRL model, I think that this relaxes the torsion. So some people would say that they think that the reason for which quantum gravity can work is that you have to allow for torsion degrees of freedom in the quantum theory. You have to relax torsion too. Because you do a path integral which is just summing over the metrics, this will have no torsion. So people say that no, don't do this, we sum over the connections and the E-fields. So this has torsion. But I don't know if these have consequences, observable consequences. But if you put matter, you have torsion. If you put fermions, you have.
Any further questions? Okay, so let's strongly thank